G'day fellow flight simmers and random YouTubers. Today I'm going to be talking about how to do fuel calculations for the A2A Cessna 172 in particular, but this of course can be applied to the 182 or the Baron. And the reason I'm going to talk about this is because most YouTubers I've seen, they basically get into their aircraft, they flight plan, and then they just fill up the tanks and away they go. Not much care is or regard is taken in with respect to fuel planning. And it's important to understand how to fuel plan because the end of the day, you don't want to be filling up 53 gallons, which the Cessna 172 can take to do a 45 nautical mile trip. So you want to basically have enough fuel to cover the trip, plus, of course, comply with regulatory authorities and or requirements, I should say, and other contingencies enabled to safely complete the flight. So, okay, so let's start. When you buy the Cessna 172, you get to these what they call performance charts. And the area today we're going to concentrate in regard to fuel planning is this chart here and this chart here. Now, this chart here, or fuel planning basically requires three phases. Your taxi phase, your climb phase, and your cruise phase. Now, A2A have very kindly, if you read down the bottom here, so for taxi, oops, what happened? Okay, for taxi you add 1.1, so you don't really need to calculate for taxi fuel. Just say 1.1 gallons for engine start, taxi, and takeoff allowance. And then your climb phase, well, this is what this table's all about, and we're only particularly interested in this section here. Okay, so that's all the rest I'll explain to you later. And then your cruise phase, you're looking to use these cruise performance charts. Okay, so let's start with this chart here. And the first thing to notice is you've got this thing called pressure altitude. What is pressure altitude? Well, before you understand what pressure altitude is, you've got to know something else. And that is international, what they call international standard atmosphere. What is international standard atmosphere? Well, international standard atmosphere is at mean sea level, the temperature is 15 degrees centigrade, and the standard pressure, which most of you people know, is 1013 hectopascals. A lot of people don't know that the standard temperature is 15 degrees. And for every 1,000 feet increase in altitude, the temperature drops 2 degrees Celsius. That's very important because if you come back to this chart here, you see here this temperature and you see 15 degrees. And for every 1,000 feet that you go up, it drops by 2 degrees, as you can see here. Okay, so if we go back, so the main function of ISA is to calibrate the altimeter so it matches up certain air pressures with the correct altitude. And with the altimeter set at 1013 hectopascal, an altimeter, which is this thing down here, will display the height that corresponds to an altitude international standard atmosphere, and this is known as the pressure altitude. Well, what does that mean? Okay, so if you, for example, you're at Moorabbin, or let's make it easy. Let's say you're at Melbourne, and you know what you want to know what the pressure altitude is. What you do is you dial in the standard atmosphere, which is 1013, and you can see here this is called the Colesman window, and you dial in 1013, and then you read off here what your altitude is, and this is called the pressure altitude, and it reads 350. Now, you know, most people who fly out of Melbourne know that the actual airport elevation is 434 feet, I think it is. But you see here, because of the QNH at that particular day, it might be 1016, and we'll talk about that later on. The pressure altitude has dropped down to 350. So that's one way of calculating the pressure altitude. Another way is you've got this formula here, and this basically tells you that the pressure height equals the airfield elevation plus 1013 minus the QNH that day times 30. Now let's say, for example, on a particular day in Melbourne, the METO reads so and so, and the QNH that day is 1023. So you plug in the numbers, and you can see by doing all the calculations, first of all, you've got to work out that part there, which gives you minus 10 times 30 is minus 300, 434 minus 300. So because it's such a high QNH, the pressure altitude that day is 134 feet. So if you go back here, if the pressure altitude, or correction, if the QNH in Melbourne on that particular day, 1023, I think I said, you would see this indicating with that at about 124 or whatever it was, 134. So they're they're ways to work out the pressure altitude. Okay, so knowing what the pressure altitude is, we go back to these charts. Okay, now 134 feet in this particular thing, you'd assume it's at sea level. So for the purpose of the exercises, I'll go through and I'll actually take a scenario. And what we'll do is, the scenario we'll be doing today is we're going to go from Melbourne to Albury, which is up in the northeast. And you can see it's a beautiful day in Melbourne, Cav and we're going to assume it looks like it's basically good weather all the way, and we're going to use what they call pilotage. In other words, we're going to take up a bearing and we're going to fly straight to Albury. We're going to fly VFR, but we're going to use what they call pilotage, which is one way of flying VFR. Another thing is called dead reckoning. Or have I got those two around the wrong way? Oh, sorry, dead reckoning. We're using dead reckoning. Pilotage is just looking out the window. Okay, so the first thing you need to do is, as I said, if you can see that, I'm not sure if that really is showing up. You can see that the conditions in Melbourne, the temperature, if you can look at that METAR, is the winds are 120 degrees at 6 knots, Cav, and the temperature is 25, and the QNH is 1015. Okay, so temperature is 25 degrees, and QNH is 1015. So the first part of fuel planning is taxi fuel, and as we saw before in that note, you don't need to work out your taxi fuel. You basically A2A, or look at the pilot operating handbook, you allow 1.1 gallons. And so what's the next phase? The next phase is you need to work out your climb fuel. Now, before we can do all that, we need to work out the pressure altitude. Okay? And by doing that formula, we said using that formula back here. Oh, sorry. By using this formula here, sorry, put in the numbers, and we get the pressure altitude at Melbourne is 374 feet. So 374 feet, in this case, we'll assume it's closer to 500, because unfortunately, if you look in the tables, it only gives you sea level 1,000. So the purpose of this exercise, we'll say it's closer to 500 than it is to 0 or 1,000. So in that way, so we've got to use what they call extrapolation. So as I said, we're only interested in this section of the table. So 500 just sits obviously in between there. So the time between 0 and 1, if we average it, it's 0.5. And fuel used from 0 to 0.4 is 0.2. Sorry about all this. And distance 0 to 2, the average, if we extrapolate for 500 is 1. Now the reason I've done that is because in our scenario we've decided to go from Melbourne to Albury, and we're going to be climbing because we're VFR at 5,500. Okay, because we've looked at the weather and we find that that's probably the best as far as the winds. They're more favourable winds at 5,500. So we're going to be climbing to 5,500, which sits between obviously 5 and 6. So we've got to extrapolate. What does 5,500? Well, time is 9 in there because you've got to average those two, and that gives you 9. The average between 1.8 and 2.1 is 3.9 divided by 2, which is about 1.95. And the average between 11 and 14 is 25 divided by 2. It's going to be 12.5. So for the climb phase, we're going to be taking half a minute to 9 minutes is going to be 8.5 minutes. So if we go back here, we can put 8.5 minutes there. I'll just move this off to the side. For the fuel, it's going to be 0.2 subtract 1.95, or 1.95 subtract 0.2 is 1.75. So 75 gallons, and the time from 1 subtract 12.5 is 11.5. Okay, so basically that's the basic calculation. However, there's some things aren't always that easy. Down the bottom here, you'll see increase time, fuel and distance by 10% for each 10 degrees above standard temperature. Why is that? Because temperature has an effect on performance in aircraft, and it reduces. The higher the temperature, the less the performance capabilities will be on the aircraft. And as you guys flying jets, you know that really hot temperatures, it takes a lot longer runoff to get in the air than on a colder day. So in this particular day, it's 25 degrees at Melbourne. You sure I'm in the right city? It's 25 degrees. You can see the METAR, it's 25 degrees, if you can see that. So how does this work for us? Well, your temperature effect is 25 degrees divided by 10 degrees, and it's a 10% increase because, as we saw here, increase time, fuel and distance by 10% for each 10 degrees above. So the effect of that is that there's 25 degrees divided by the 10 degrees times 10 10%. So it's a 25% increase in your times, fuel used, and distance. So now we worked out the time here was 8.5, and we've got to multiply that by 1.25 because it's a 25% increase. So if I get my trusty calculator here, and so 8.5 times 1.25, 10.65. Or 6.2, sorry. We'll call it 6.3. 10.63 minutes. So the time to get to your cruising height will be longer. The fuel used is going to be 1.75 times 25%. Roughly 2.2. And the distance is going to be 11.5 times 1.25. 14.4. Okay, so it's going to take us just over 10.5 minutes, 2.2 gallons of fuel, and 14.4 nautical miles to get to our cruise. So we've taken the temperature effect, what I call the temperature effect, to get our cruise. Okay, so now we got to our cruise. So let's just get rid of all this. This is where cruise performance comes in. Okay, so now we look at this, and the first thing you think is, what is all this about? Okay, 20 degrees below standard temperature 20 degrees above. Well, thank God we've got this. We can use a SkyVector for this, and I'll talk about that later on. But we know that between Melbourne and Albury is 140 nautical miles. Okay, so and we know we want to fly at 1,000. At 5,500, but we don't know our speed. Okay, so we go back to our charts. And the first thing you've got to do is, you're at 5,500. We're going to be looking at this particular. We're going to be looking at 6,000 because 500 is not going to make a much difference. Now, what RPM are we going to operate, or more importantly, what horsepower we're going to? Because if you're going with more horsepower, you're going to put a lot more wear and tear on your engine. I personally like to keep the horsepower around about 70-75%, which is either that or that. Which 70% brake horsepower, which is up here, equates to 2,200 revs, and I find that is just a lovely. You're not going to get there in a real rush, but you're going to be using a lot less fuel because, as you can see, the higher the revs, obviously, you're using more fuel. Now, the other thing is, what do? Do we look at that column, we look at that column, or do we look at that column? Well, this is where SkyVector comes in handy. Just by pressing navlog here, and looking at sky vector, you can see Melbourne to top of climb. This is our climb phase, and top of climb to top of descent is our cruise phase. So we're interested in this sort of set of numbers all along here. And you can see that the temperature at 5,500 is going to be 11 degrees. So that equates to, and they've see the deviation, that is ISA plus 7. So you don't have to work it out. There is a way of working it out, but you can see it's ISA plus 7. So with that in mind, this is ISA plus 20, and this is ISA minus 20. We got plus 7. Okay, so what do? We can do the really long-winded way and going sort of extrapolating. Say if we decided to use this particular horsepower, 71 or 2,200 revs, really. You can use those set of numbers because you're ISA plus 7. Let's say it's ISA plus 10. So you've got to sort of work out the average between those numbers and those numbers. Now, I prefer not to do that much working out, otherwise you'll be here forever. I always err on the side of caution. And I know that if I go down to use standard temperature, the calculation will involve over calculating fuel. But it's not going to be that much because the difference between standard temperature and your fuel used, which is gallons per hour, 7.7 there and 7.3 there, it's only 0.4. So I'd rather carry a little bit more or less. Rather than trying to work out the average between those two, I'll assume that we're going to be operating at standard temperature. ISA and ISA plus 7 is not much. If it's ISA plus 18 or 19, then obviously I'd use that column. But today we're going to use that column. So we've decided to use 2,200 revs for our cruise, and these are the figures that we're interested in. So you can see, we're not interested in those figures. These are the figures we're interested in. So we can see that we're going to be cruising at, this is true airspeed. Always in fuel calculation, you're going to be using true airspeed. We're going to be doing 111 knots. Okay, so you come back here. Now we know that between Melbourne and Albury is 140 nautical mile. But of that 140 nautical miles, the 14 of that 140 is going to be used for your climb. So therefore, you're going to be, for your cruise, you're going to be using 140 subtract 14.4 equal 125.6. Okay, 125.6. nautical miles. Okay. Now your speed. Okay, what's your speed? Is it 111? Well, no, not really, because you've got to take in the upper winds. How do I find the upper winds? You've got this sky vector, and as I said, this gives you the wind direction and your speed. Now we're going to be travelling in a sort of northeasterly direction, but today's winds are 261 at 10 degrees. In other words, they're coming basically from the opposite direction. So we expect we're going to have a hell of a tailwind. Okay, and we can see that because we can see that our ground speed today will be 143 knots. And you can see that, hang on, I've just done something. I'll put 111, sorry. I forgot to do something. Do another navlog. Okay. So our true airspeed here is 111. But because we've got basically a 10 knot tailwind, that's kicked it up, and we're doing a ground speed of 119 knots. So we've got basically got an 8 knot tailwind. Okay, so how does that affect us? Well, in our calculations, coming back here, what was it again? Bad memory. 119. So we've got 119 knots, we're doing as true airspeed. So that's going to affect the time and the amount of fuel we use. Now, what time does it going to take us to go, as we worked out here, 125.6. So we go 125.6 divided by our speed, which was 119 knots. Let me work that out. 125.6 divided by 119. It's going to give us just over 1 hour, 1.05 hours. Okay, so by travelling 1.05 hours, how many gallons of fuel we use? Well, it says here we're using 7.7 gallons per hour. We might be using a bit less because with ISO plus 7, and as you can see, with the higher the temperature, the less fuel. But we'll err on the side of caution. We'll say we're going to be using 7.7 gallons per hour. Therefore, 7.7 gallons per hour times 1.05 it's going to give us about 8.13. So 8.13 gallons. Okay, so now we've worked out our taxi fuel, we've worked out climb and cruise. So basically worked out how much fuel we need for our trip. However, there's another thing that you need to worry about, because the thing is, you might get in your aircraft, and you take off and you fly, and you're flying to Albury, and you're descending. You probably just taxi off the runway, and bang, your fuel will stop because you've worked out just enough fuel just to get to Albury. However, there's a regulatory requirement that's fixed or required by CASA. It's called fixed fuel reserve. Now, I think it's just recently changed. It used to be 45 minutes of reserve, but if you're just an RPT or just a recreational pilot, it's now come down to 30 minutes. If you're doing IFR, then that's 45 minutes, and I can't find the document at the moment. So you need 30 minutes of extra fuel. So 7.7 gallons, we've worked, shows you here, 7.7 gallons times 30, you need to carry another at least 3.85. So if you want to do the trip from Melbourne to Albury, if we add up all this time, 1.1 plus 2.2 plus 8.13 plus 3.85, we'll add all that up. We need about 15.3 gallons of fuel, basically, to go and to get to Albury and also have some reserve fuel, because basically the law requires that you have reserve fuel on board. If you start dipping into your reserve fuel, then you're in trouble, and you actually have to declare an emergency. So I hope that clears it up to some point in regard to proper fuel planning. And I guess, like I said, I mean, you can get into your Cessna and fill up the tanks, but that's no fun. It's a lot more fun actually trying to work it out as they do in the real world. All right, I think that's about it from me. It's starting to get up to about 35 minutes. So I hope that clears it up. I'll put some, well, actually, I don't need anything in the comment. I look forward to your comments. And till next time, see you later.